Hello and welcome to my video proving Riemann's rearrangement theorem. Uh, so I'm not going to do any examples of rearrangement to show why this is necessary. This is more just like a strict proof video, but I will go really quickly over what does it say. So Riemann's rearrangement theorem states that you can only rearrange an alternating series if and only if it is absolutely convergent. Um, so you might be wondering what does absolutely convergent means? Well, say we have an alternating series and its non-alternating counterpart, then the alternating series is absolutely convergent if and only if both of these series converge. Um, Another way to think about this is just is the absolute value of every element in the sequence added up, is that convergent? So this really only applies to alternating series because obviously a non-alternating series will be absolutely convergent because it already is like the absolute value every element. So yeah, so on to the proof. This might not make sense at first, but just bear with me. I promise you it will in the end. So just again, say we have an alternating series. We can decompose that into two sub-series, as I'll call them, or subsums. Uh, one that deals with all the positive elements and one that deals with all the negative elements. You'll notice that the one that deals with the negative elements uh, will only have the odd n input, and that is because -1 to an odd number is -1, so that negative sign accounts for that. And then say we also have very similar to the alternating series, except it just doesn't alternate, so we also have that series. Well, we can decompose that similarly, this time just with no negative sign because it doesn't alternate. So yeah, um, the series is absolutely convergent. It is not absolutely convergent, but the alternating series does converge. So that means this doesn't converge, this does. So yeah, there are four possible options for the subsums. Either both of them converge, only one converges, or both diverge. And that is four because uh, either one could converge in the example where only one converges. So yeah, let's run through these options and see if they're possible. Let's try both converge. Well, we have our alternating series, and we can decompose it into the two subseries. And if both converge, this would be a finite number minus a finite number equals a finite number. So okay, this one does meet the conditions we need. How about if we have its non-alternating counterpart? Well, this would be a finite number plus a finite number, which would also equal a finite number, which we don't want because remember, this is non-absolutely convergent. So no, this one doesn't work. But it would if it was absolutely convergent, if this alternating series was absolutely convergent. So that's just a nice, interesting fact. What if just one converges? Well, then we would have the alternating series. We would again decompose it, and we would have either a finite number minus infinity or infinity minus a finite number. Either way, it diverges. Um, and remember, this one needs to converge, so no, does not work. And then just, looking at the other one, the non-alternating counterpart, it would be infinity plus infinity, which we do want, but still, this one does not work. So our final option, both diverge. Well, again, say we have the alternating series. We decompose it, and then we would have infinity minus infinity. Both subseries diverge. Um, okay, so that does work. Infinity minus infinity can boil down to a finite number. And then say we also have the non-alternating counterpart. We would have infinity plus infinity after, decomposing it, which also meets our criteria. So great. Uh, for a non-absolutely convergent alternating series, both subseries, are they have to diverge. So yeah, back to the proof, and this may be a little bit confusing at first, but just think on it. So again, looking at the alternating series, we can decompose it into infinity minus infinity. And you might be saying, okay, well this doesn't inherently mean that we can't rearrange it, but the idea here is it's just a series, so you can take a bunch of, and remember, for an alternating series, the test is that if this a sub n, if it decreases monotonically, that means the derivative is never positive, then it works. So it's always decreasing. So that means that you can just take a few smaller numbers and a few larger numbers to create a nice even number, and then do that for both series and just kind of create oscillations between the two series. So first you make a large number out of pieces values from this series, and a number slightly smaller from this one, so you get a positive number. Then you'd make a negative number from this one, an even larger one, and you get a negative. And then you make a positive one from decomposing elements from this subseries to get a positive one. And you just slowly focus down onto the point which you want to have, the number that you want to get, so that you've rearranged it basically to be any number. I apologize if that was an awful explanation. I'm new to this, but just think on that for a little bit. Yeah. Yeah. Anyway, so the really interesting thing here is, depending on who you ask, I've met a few people who disagree, but pretty much depending on who you ask, if you ask me, you can find if an alternating series converges, just not onto what, which I think is really cool. Yeah. Thank you for watching. I know this video was a bit of a doozy. Hopefully it was easy enough to understand, but yeah. Thank you for watching.